So today we have the pleasure to have with us Danai Deligeorgaki from KTH Royal Institute of Technology in Sweden, and she's going to give a talk about colored multiset Eulerian polynomials.
Yes, perfect. Exactly. I'm going to talk about a combinatorial topic. I hope that's okay. I know you are experts on also different areas, so I'm hoping that you will just interrupt me and ask me questions during the talk about the technical details that may not be obvious to your respective fields. But the starting point would be the Eulerian numbers and the Eulerian polynomials. Hopefully some of you have seen those. I know some have. So here I have, so the idea is, I'm thinking of this set of n permutations that you can see my mouse, I think here. And then I want to consider a statistic on them, for example, the descents, which we'll see is the number of positions where the value drops in a permutation, and make a polynomial out of it where I sum through all permutations in this from these n elements, and then I take x to the number of descents for my statistic. And this forms the Eulerian polynomial. This is one way to define it. But also these polynomials arise in other ways. For example, they are, if you've seen it, they count integer points in polytopes. They arise as volumes for, again, some polytopes that are slices of cubes. They may count faces of simplicial complexes. And they also arise, through, for example, through Hilbert polynomials, Hilbert polynomials for certain rings. They're very basic, elementary. So Euler studied them in 1755 or something. He studied these numbers in relation to different stuff. And there are first few examples you can see in this board on the left, in this table. So it would be that since they are statistics on permutations, the coefficients would sum to the total number of permutations for its number. So for 3, n equal to 3, I have 6 permutations, and this is the polynomial with coefficients summing to 6, and so on. Of course, by just looking at this, you can guess that there's a lot of nice things going on. The polynomials are palindromic, so their vectors of coefficients are symmetric, in a sense, right? And then they also have the property that's called unimodality, which means, we'll see it again, they increase up to some point and then the value drops again, and many more properties. Their roots are real if you compute them, and so on. And of course, people, since they have been around for so long and they pop up in different contexts, their identities are very useful to have in these areas, and there's many of them. One of the most famous is the Carlitz identity that you see here, that has the Eulerian polynomial to the left in the numerator, and on the right it has this infinite sum with this nice generating function t plus 1 to the n. So we will also revisit that, but this is one of the main identities that are known about them. This is the style of identities that we investigate. So for today, the idea is generalize a little bit this context. So I'm going to be talking again about permutations, and in particular, I would consider a larger class of permutations that allow for having repeated entries in the set of permutations, so multisets. And I would also consider colors, which means I have some choices, even though I have for every entry of the permutation. So one example is the signed permutations. I don't know if you're familiar with any of these concepts. Right, and for those permutations, again, it's interesting to understand polynomials that arise from different statistics, such as their descent polynomials, and then these generating functions, in the sense that the Carlitz identity that we saw before had some identities of this kind. And we would do this in relation to some geometric objects, in particular polytopes that I will define, I think, and yeah, how dilating these objects, these polytopes, and taking products with each other corresponds to permutations, basically, and how Ehrhart theory, which is the theory of studying lattice points in polytopes, can help us answer questions about these permutation polynomials, like the Eulerian polynomials, how we can use it to deduce distributional properties like these symmetries and so on. Yeah, and I don't know if I'll have any time to talk about other applications. So again, it's pretty combinatorial and technical, but these are the main objects we are interested in, their permutations, this time for multisets and allowing some colors. So I'm assuming that I start with this M that has a bunch of ones, twos, and so on up to N with a positive number of its, with these cardinalities M1, M2, and so on. And then I consider the set of multiset permutations, which is what you imagine, like always to order all these elements. And I write a permutation pi in one line notation, like the ordering of the elements. And that's how I think of them. For example, for the multiset with 2 copies of 1 and 1 copy of 2, I have these 3 permutations, 1, 1, 2, 1, 2, 1, 2, 1, 1. Now, this is already a generalization, but again, I also want to add the colors to the main objects. So a color permutation, to make sense, to talk about color permutation, I need to know what are my colors. So in this case, I need to decide a color vector, let's say this R here, that would tell me how many colors do I have available for coloring every copy of 1 in my permutation. This is R1. Then how many colors I have for the copies of 2, this is R2, and so on. And from this, I can construct a color permutation. We'll see the examples, and it's a lot more straightforward in there, but the way I denote it is pi to some vector with exponent some vector denoting the color for each of the entries. And then, or I can think of it as, again, pi1, pi2 with some exponents denoting the color. And I do at the end, I do add a dummy thing like this n+1 to the 1 at the end of its permutation. It's just there. We're going to use it for descents. So it's going to be more clear for examples. And all colors, all the CIs, the colors are taking values in one of the allowed choices from 1 up to RK for color and K, the entries K. So here's again the definition, and let's see an example for what's called the sign case, where all the colors are assumed to have 2 options. So R1 is equals to R2 equal to 2. And now I'm considering the multiset with, again, only 2 copies of each element here. So now there's going to be a lot of permutations there. In total, there's going to be 6 permutations for the multiset 1, 1, 2, 2. And then there's going to be 2 ways to color each of the numbers that appear in them. And there's 4 entries in them. So there's going to be 2 to the 4 times 6 in total. But here I have written down just the first few. So the ones that follow this permutation pattern, just 1, 1, 2, 2, even though I can allow for all of them. And I've written down all possible colorings I can have. So you see, again, the 1s and the 2s, each can have a color 1 or a color 2. The 1s take value from, the colors for the 1s take value from the entries of this R1, and the values for the 2s from R2. And then I have at the end, this 3 to the 1 is just something I add at the end. I don't color it, it's just, again, it's the n+1 to the 1 that I'm going to use later for comparing for descents. So that's always there and does not move. Good. So then we want to, again, it's very basic to think about descents on these objects. And the way to define descents, it's this intuitive decrease in consecutive entries. So we will say that a descent is a position of the permutation, I, so a position of where M is the total entries in the permutation, the cardinality of the multiset. So I'm choosing a position such that whatever I have there is larger than what follows it. But to talk about comparison, I need an ordering. I need to decide on an ordering for all colored numbers. So before we had the numbers 1, 2, 3 up to n, so the ordering was induced from that. Now I'm just deciding an ordering for all the colored versions of them, and there's some choices to be made. So we're following this ordering here due to Stein-Grimson. So it would be that whenever I have the same color between two elements, the largest one wins, and whenever I have different colors, the largest color is more important. So the copy of 1 with color 2 is larger than the copy of n with color 1. This is just our ordering and our way of deciding what's a descent. So here in the same example as before, I would have, for example, now I can look at and decide what is a descent and what is not. So the first position is a descent because 1 with color 2 is greater than 1 with color 1 in my ordering. And then nothing else is a descent until the 4th position, where, again, the color here for the 4th entry is greater than the color for the 5th entry, and therefore it forms a descent. In the second, here on the right up, there's no descent. On the right left, there's 2 descents. On the bottom left, on the bottom right, there's 3 descents, and so on. So it could be like lots of different numbers of descents appear. It could be from 0, like you see here upright, up to 4 in this case, or n minus 1 in general, because, n in general, because all positions of the permutation can have a descent, or m, whatever it is. All the positions can have a descent, and except for these 3 at the end. This can never be a descent because there's nothing after it to compare it to. So one idea is to study the polynomials again that arise for these descents of permutations. So how would I do this? I would group together the things with 1 descent, the things with 0 descents, with 2 descents, and then count how many there are in each case, and this would be the coefficients of my polynomial. Or in other words, I would come here to define, let's say I would, with small letters of des, we usually denote the number of descents we have, and with capitals, it's the set of descents, the sets of positions. So now I'm interested in the number of descents that I have in each of the permutations. So I would sum over all permutations that are colored for my choice of set and coloring, and take the term x, the monomial x, to the number of descents that they have. And this would be called the colored multiset Eulerian polynomial, because when I specialize the set to be just the numbers from 1 to n, and the coloring to be just a vector of ones, so basically no colors, means just one choice for each coloring its entry, so it's the vector of ones, then I recover the Eulerian polynomial. And these are the objects that we are now going to study. So let me know if something is not clear of how to form them. They're just, I sum over all colored permutations, and I look at their descents, and then I take this very natural polynomial that arises. And I have some examples. So the first example is this multiset with 2 copies of ones and 1 copy of twos again, and no colors. And this is just to show you, I mean, the colors are the vectors of 1. And there's going to be, again, only 3 elements here. And these are the possible descents. So the descent polynomial would be 1, because I have 1 thing with 0 descents, plus 2 times x, because I have 2 things with exactly 1 descent. And a bit more complicated example, if I take 2 copies of its number in the multiset and allow for 2 colors for the ones and 1 color for the 2, then I get all these permutations. And out of these, one of them has no descents. This first term is always 1, the constant, because there's only one way to order everything in an increasing, non-decreasing way. Then I get 13 with 1 descent and 10 with 2 descents. So already you can see that when we generalize to this setting of, for example, multisets, in the first example, even with no colors, the palindromicity is gone. And the same with the colors on the second one. So the first, So it's not necessary that these numbers will anymore be, these polynomials will be palindromic, but they may satisfy some of the other nice properties, like the fact that the unimodality, that the coefficients increase up to a point and that they drop, the roots here are real, and so on. So our objective was to study these polynomials and see what we can say about them from this perspective. And yeah, this is just a quick slide, like in case you have seen any of these terms. So because we're talking about enumerative combinatoric stuff, the goal is to understand inequalities that hold among coefficients of our polynomials of interest, like the examples that I mentioned. So given a polynomial, let's say here of degree p with coefficients p0, p1, and so on, I want to ask if it's palindromic, which would mean the vector of coefficients is symmetric. If it's unimodal, which is, as I said, increases and then decreases. If it's log-concave, which imposes another inequality between its coefficients. Then we call it gamma positive if it's palindromic, and then I can express it in a different basis that you see here with the xi's, and these coefficients there are non-negative. Not too important, but I'll revisit this. Real-rooted is called when all its roots are real numbers. There's another property called alternatingly increasing that compares its coefficients again. And even more, so the other thing we study is, so these polynomials are not necessarily palindromic, but they have a property all polynomials share that is really nice. So every polynomial, let's say of degree d, can be decomposed into a sum of two polynomials, a of x plus x times b of x, where both the a and the b are palindromic. The a is palindromic with respect to degree d, it's of full degree, and the b is palindromic of smaller degree. And with respect to degree d minus 1. I mean, it doesn't matter. So it's an exercise that every polynomial you take, you can, even if it's not palindromic, you can decompose it in this way into its symmetric decomposition, as it's called. And then we go there and ask, since even for non-palindromic polynomials, we have these two other polynomials that are palindromic, we can study them and ask again, are they unimodal? Are their roots real, or are they gamma positive? Since they're palindromic, it makes sense to talk about gamma positivity for those, and that when both of them are gamma positive, our original non-palindromic polynomial is called bi-gamma positive. Bit of technicalities you don't need to worry about if you haven't seen it. And one more point for these properties. Now is the interlacing property. How does this work? So if we have two real-rooted polynomials, say p and q here in this slide, with roots alpha n alpha d, beta n beta n, we want to ask how their roots interact, basically, like one with respect to the other. If they alternate, like here, so we have first a root of p, then a root of q, then a root of p, then a root of q, and so on, we say that, in this case, q interlaces p. One interlaces the other. So the one that has the second root interlaces the one with the first root. Yeah, and this is an important property that connects to the ones we just saw. So for example, if I have this polynomial p, that is an example of an Eulerian polynomial, 1 plus 4x plus x squared, and q, which is an example of the Eulerian polynomial for n equals to 2, 1 plus x, then we have that q interlaces p. Because if I compute the roots, they satisfy this sandwich property. Now, there's also non-examples, and they even arise as polynomials in the symmetric decomposition of colored multiset Eulerian polynomials, and this is one example here. So if the p is chosen to be just 1 plus x squared, then it has non-real roots because its discriminant is negative. And that means we cannot talk about interlacing even. It does not interlace with q. Right, so the interlacing property is very, very strong in the sense that with the condition that the coefficients of these a and b polynomials are non-negative, which holds in our case often, it implies all the properties we saw. except perhaps for palindromicity. So if I show that a polynomial, I take my polynomial a here, AMR, and I show that in its decomposition, the B interlaces A, then I have that all my initial polynomial AMR, also the A and the B, they all are unimodal, log-concave, gamma positive, real-rooted, or bi-gamma positive, and yeah, alternatingly increasing. So it's one stronger way to show these properties. And that's how we are working in this project. We proved that this holds for a class of polynomials so that we get out all these nice properties. And because these are natural generalization of Eulerian numbers, they have this they do have this strong property that their roots interlace still. The Eulerian numbers, the Eulerian polynomials also have it. And our polynomials still have it largely, except for small cases that we'll see, for small cardinalities. Yeah, so this slide is not, as I said, is just saying, giving the examples of when the two polynomials, the symmetric decomposition of a colored multiset Eulerian polynomial can have the interlacing property that we saw or not have it. So it's just the example we saw before, corresponding to some multisets. Great. So far, we have seen how the things, we have seen what the goal is. It's to prove these distributional properties. But the tools now, there would be identities, like for Eulerian numbers. And one type of identity is this Carlitz type identity. So that was in the first slide for numbers. So I want to generalize this to multisets. And I think, yeah, this is the right generalization to multisets. So again, I consider a multiset and a vector of colors. And it turns out the Eulerian polynomials for these on the left, they again have this nice connection to a generating function. And the generating function is nothing else but a product of binomial coefficients. Before it was t plus 1 to the n. Now it's a bunch of binomial coefficients, but n of them multiplied with each other. So in this is just a table that says what happens when I'm not in a multiset case, so all the multiplicities are equal to 1, then I'm just restricted in the first row. And this example, the first one, up and left, is what the identity of the Eulerian polynomials is. It's what the generating function, the generating series would be. And it turns out this thing generalizes. So even if I think about colors, so this was the uncolored case, if I move to having 2 color options for everything, then I get again a nice generating function and so on. For 3 colors, I just get a 3 in front of t and so on. And when I think about multisets with higher cardinalities, so for example, everything has 2 copies, then I just take a product of 2 things with each other to the end. And the more copies, the more products I take. And the more colors, the more I change the coefficients in front of the t's, but that's all that happens when I generalize to colors and multisets. Yeah, so that's the first identity that one can prove just by generalizing what is known. Of course, there's a lot of work in this area, and there's identities like that for multisets, for colors. So we did give a multivariate version of this. This is the same identity that specializes to what I just said. And then in combinatorics, it's interesting to find several kind of identities like Q analogs, what is called. So sometimes you just work with 2 variables and there's this other statistic, the major statistic, and you try to associate the distance and the major statistic at the same time and find an identity there. So this thing exists for our setting as well, and so on. But we are interested in the very special case, no more than 1 variables, and this is the last equality here. So I'm just telling you, we did it in a more general frame to recover a lot of other identities as well. So this is our tool. This last line is now what we're going to use for proving it. And before that, I'm going to tell this again, that there's several identities in combinatorics, that this is now a different. So we have another identity that we found as well that generalizes perfectly the Karolidze identity with the MADs here. Other people's work that you may have seen, but I'm just going to skip this slide and go back to a summary of what we saw so far. Yeah, so the Eulerian polynomial is what we are interested in. It's generalization to color multiset anyway, this AMR, and it has a decomposition into two symmetric polynomials in this way, and we want to understand its distributional properties by using this identity at the bottom. Any questions? I'll take 30 seconds pause. Perfect. So we're going to do this through polytopes. Because it turns out in the world of polytopes, these numbers also arise, both these sides of the inequalities. So polytopes, you must have seen before. They can be thought as the convex hull between some points in RD, like finitely many points in RD I take and I get the convex hull, or I take hyperplanes. So the polytopes would be intersections of closed half spaces in the space, as long as they're bounded. So the cube is an example, and it arises as the convex hull of its vertices, or it arises by taking these like 6 hyperplanes that cut it in R3. And the most standard example of polytopes is maybe the simplices. So that means I am in RD I'm in RD and I have D points there. And that gives me a simplex of dimension D minus 1. So in R2, in the plane, I take the convex hull between the two unit vectors, and that gives me this standard simplex of dimension 1. Then in R3, I would take the convex hull of the 3 unit vectors, and that's the standard simplex of dimension 2, and so on. Then starts it's the pyramid, the tetrahedron, and so on. Now, if I talk about dilates of a polytop, it means I take the kth dilate is I take all the points in the polytop and I multiply them with k. So in the example of the one-dimensional standard simplex, I would be instead thinking of 2 times the points in there. So I would be taking the convex hull, or the line here, the interval between the unit vectors, it's multiplied by 2. So dilated polytopes just means multiply all the points in there by k. So with this in mind, we can talk a little bit about Erhard theory, with some people here work on. So the idea is now that we want to think about polytopes, but the vertices of the polytopes, we want them to have integer coefficients, to be in ZD. And that's because it's an integer. It's this area studies integer points, so you need to start with things that have integer vertices. Now Erhard in 1962, he studied what happens when I take a polytop, I dilate it by something, by k, and then I look at the integer points that it has. So in its boundary and it's inside it. So the number of integer points in the kth dilate. And this turned out to be given by a polynomial. So there is a polynomial such that for each polytop, there's a different polynomial, or not necessarily different, but there is a polynomial such that when I evaluate at k, it gives me the number of integer points in the kth dilate of the polytop. And this is easier to see in the example here. I have for example, the standard simplex of dimension 1. This has 2 points, the ones on the boundary. Now I dilate it by 2, I get this other one, This has 3 points. I dilate by 3, I get 4 points, and so on. So the polynomial would be just k plus 1 in this case. And if I wanted to dilate, if I started instead, not with delta 1, but r times delta 1, for example, consider here 3 times delta 1, the pink one, and I dilate by 2, then I hit the 6 times delta 1. So the first one had 4 points, the second one has 7 points, and so on. So the polynomial in this case, the Ehrhart polynomial is r times k plus 1, 3 times k plus 1. Okay, so this is how we compute Ehrhart polynomials. There are also formulas for, like we can see in a similar reasoning, we can also count points in higher dimensional simplices. For example, in triangles, it's not too hard to find out the formulas. Triangles, tetrahedra, and so on. So for a d-dimensional simplex in general, it's going to be k plus d choose d. It's the number of ways to put the k balls in the boxes, or vice versa, with repetition. Yeah, and this specializes, if you take d equal to 1, it specializes to the previous case where the dimension is equal to 1, and I just have k plus 1 here, right? Now, more generally, if I take a dilate of the d-dimensional simplex, again, just the r appears in front of k and nothing else changes. And one more example I have. Just a second, because there's noise here. Close the window. The cube or the square. Let's look at the square. The polynomial, the Ehrhart polynomial of the square, so you can see it from the picture, is just k plus 1 squared. So the first dilate has 4 points, the second dilate has 3 squared points, and so on. And the colors again behave accordingly. And more generally, if I take the d-dimensional square, the Ehrhart polynomial will be k plus 1 to the d. And that's because a square is nothing else but a product of intervals with each other. So the square is k plus 1 squared because it's a product of 2 intervals. So the Ehrhart polynomial of the product of 2 intervals is the product of the Ehrhart polynomials of the intervals themselves. And each interval has Ehrhart polynomial k plus 1 squared. So basically, the Ehrhart polynomials have this very nice property that, now this is a bit compact notation, but it's saying that if I take a polytope, so for example, a simplex of dimension m1 dilated by r1 times in the polytope sense, it means the Cartesian product of all the points that can arise if I consider the points in its polytope. Anyway, times r2, delta m2, and so on. So a product of a bounds of dilated simplices of different dimensions. Then the Ehrhart polynomial of this whole thing, of this polytope, it will be a product of Ehrhart polynomials, each of a dilated simplex of some dimension. And that means it would have this form here. And that's exactly the form that appears in our theorem. So when we look at this theorem, this left part, this equality that we had from before for the Eulerian numbers, and we see this product, we can think, but wait a minute, I have an interpretation for these coefficients that's the same as counting integer points in products of dilated simplices. And that means in particular that by definition, this is just an Ehrhart polynomial. So we make this connection to polytopes and Ehrhart polynomials from this previous tool, from this previous identity. And the idea then is to use this connection and the polytope, the geometric realization, to derive the distributional properties, because it's easier. There is a way to look at how one fits inside the other in the space, and then you can deduce more easily your theorems. There are tools there. So in particular, what we need from polytopes is some theory that says that the polynomials in the symmetric decomposition that we had from before are non-negative, and we get that just from the connection to polytopes. but I'm not going to get into too much detail. So what happens is that this identity that I just talked about implies that, well, with some restrictions to the values of colors with respect to multiset cardinalities, it means that basically my polytope will have an interior point. And therefore, since it has an interior point, it just follows from the theory of polytopes that the B polynomial will interlace the A polynomial for the colored multiset-Eulerian polynomial. And that means all the distributional properties we talked about holds. So that's our result. It's the connection to polytope, and that the interlacing property then can be applied to derive things for the colored multiset-Eulerian polynomials connected to permutations. And also we can use the polytopes as well to understand exactly when these polynomials are palindromic. So we characterized when they're palindromic based on the polytopes, and this happens for specific color vectors with respect to multiplicities here. So how does this work? This is more for the experts. So the idea is that, I mean, you don't have to worry about the proof, but this is the table from before. And the idea is that we identify this diagonal here. In a sense, we identify for its color, for its multiset, let's say, we find a color vector that the polynomial becomes palindromic. And after that point, we use these interlacing techniques to show that from that point onwards to the right, everything will be palindromic. So we find something here, everything will be, they will interlace with our palindromic polynomials in a sense. So it just suffices to study that these are the palindromic ones. What happens before? So these are the cases I was excluding. We don't know. It's not necessarily true that this strong property of interlacing holds before this diagonal. So this is a separate case of study before the diagonal. We just showed it for after the diagonal. So what can I say now? Maybe I'll skip the proof parts. And then I would say that there is this gamma positivity considerations that for the cases from before, from this column in the table, we know in this column, in the uncolored case and just multisets, we know exactly when the polynomials here are palindromic. And this is exactly when all the multiplicities in my multiset are equal to each other, and in no other case. And then for the other cases that are not palindromic, we want to understand the symmetric decomposition. And in particular, the question now is, are these the polynomials in the symmetric decomposition, are they gamma positive? So are my polynomials basically bi-gamma positive? And find combinatorial interpretations for the coefficients, because that's something we do a lot in combinatorics. When I have a polynomial that I know its coefficients are non-negative, then I look for a natural interpretation for them in terms of my objects. So for example, for permutations, the gamma coefficients count like something like peaks or double descents and so on. I want something like that. So another result we obtained is for a special case of a multiset where I have the same copies of all numbers, and then at the end, one extra larger number, so an n+1. For this multiset, but it doesn't have palindromic or colored multiset-Eulerian polynomial, we did look at its symmetric decomposition into two polynomials. One of them was studied before, and it was shown to have an interpretation in terms of some trees, certain weakly increasing trees, whatever that is. So we found a combinatorial interpretation for the first one as well, for the polynomial A in terms of these trees. And the purpose we did that is so that we can provide a kind of a bi-gamma positive combinatorial interpretation, so interpret both of them and pose the question that says, we have an example of a gamma interpretation for A and B for a very special case. Can we do this for more cases. And in particular, from our theorem, there's this whole class of polynomials we just studied, and we showed that they have this interlacing property. So we showed they're bi-gamma positive. So the question is, can we bring this method somehow to the more general case to cover all these polynomials? If we did this, it would be nice, and it would also ask the similar question Athanasiadis answer the similar question that Athanasiadis asked. So Athanasiadis asked this for just colors and not multiset. So I'm not sure, maybe I go here. Athanasiadis asked the bi-gamma positivity of this line. We're asking the bi-gamma positivity of all of these, which we know they're bi-gamma positive, but we just want an interpretation of their coefficients, and they're very tricky to find. So that's one thing that is now open from this work. And yeah, just to show you that it's nice. So here's one example. So what have I been doing with these polynomials? This is just one example where I start with a special multiset and no colors in this case. And I look at the descent polynomial. I get this polynomial 1 plus 12x plus 15, x squared plus 2x third. Then I look at the symmetric decomposition. That's what this is doing. It's decomposing into 2. And as I said, there's a unique way to derive this. And then I take each of these, and I write it in terms of its gamma basis. So this is what happens here. The first line is the A in terms of its gamma basis. And with the interpretation, it's just counting certain trees that I have here. And I do the same with the B. So I end up like just decomposing the polynomial in a different basis overall, in a different way, where each of the coefficients has a meaning. So you can derive it by counting trees with certain properties. So we would like that for more polynomials, is the idea, and find a more universal theory there. Because these polynomials, they generalize the Eulerian polynomials and they include them, and there must be a natural way to do that. Then I would, I don't know how much time I should take. There's some connections to order polytopes, to statistics polytopes, to S-lecture hall polytopes. So I tell you the statistics one that maybe you haven't seen before. Very quickly. Okay, so some connections to statistics. I have discrete variables, a bunch of them, and they have, each of them has some outcomes, M1, M2, and N of them. And then I want to build a model from them. So for variables, I can define, I'm from the combinatorics perspective, so we just want to use some object, like a geometric object, here a simplicial complex, to define a statistical model for our variables, so that then it has nice properties, if that makes sense. So by simplicial complex, I mean a bunch of simplices glued together such that they only intersect at faces and so on. So this on the left is an example. This is a non-example because I don't just arbitrarily glue something to the middle of the triangle. I just want to intersect on vertices, edges, and so on, if they intersect. Now the log linear hierarchical model, whatever that is for the simplex and the variables, is defined as some vectors in a simplex of dimension the same as my possible number of outcomes in total, so the product of the outcomes of the variables, -1 because I'm doing probabilities, I want them to sum to 1. And it's open because I don't want to consider the zeros. I want to consider everything positive, all probabilities positive. And then the way to define it, I mean, it's just that I somehow take into account the structure of the simplex. So to find the probability of something, I look at then how these outcomes behave based on the facets of the simplices, which means I just go through the simplices and somehow take it into account when I define the model. Maybe that's a bit vague, but it's just, I want you to remember from a simplex and some variables, I can take out a model. Here's an example. This is the trivial example with 2 points not connected. It's still a simplex. It's 2 simplexes of dimension 1, so it's a simplicial complex. And there's two, in theory, I decide now there's two outcomes for each. So it's a binary variable case. Now, the model will have all distributions that are positive, where x1 and x2 are basically independent. This is the independence model on the positive part that you may have seen before. In other words, I want vectors, I want to account for two possibilities for each of the entries, so p11, p12, p21, p22, and I want that I can express them into these products of two. So they're kind of independent. So that means the probability of 1, 2 happening is the same as the probability of 1 happening times the probability of 2 happening. So that's what this is basically encoding, this factoring rule, this model. There's more complex examples. And the idea anyway is that for these models, the models are themselves subsets of the simplex. So people started looking at what these subsets can look like. And when I have defined the models in this nice way with a simplicial complex, they're just intersections of the simplex with a variety. In fact, a toric variety. And that means there's a polytope there. Because in every toric variety, there's a polytope associated to it. Don't ask me how. But even better, you can read off, like, you can basically look at this simplex I have here and understand exactly what the polytope associated to the model is. So for every model, which just means to me simplex and number of outcomes, simplicial complex and number of outcomes, I have a polytope out that I can read off. This is the convex hull of some bunch of sums of unit vectors that I can read off somehow. And it's telling me, the polytope is telling me things about the model. So it makes sense to study the polytope just to understand the variety intersecting the hypersimplex, which is exactly my model. And that's something we are doing. So you can study the polytope and then you can use this to check if a vector summarizing data is coming from the model you have. If you have a given vector of data, does it come from my model that I constructed or not? Then some maximum likelihood estimate stuff and maximum threshold stuff. But in polytope language, what this means is I want to understand the volume of these polytopes, whatever a volume, you probably know what this means, and triangulations of these polytopes. Intuitively, you get an idea from the word what this means, and the degree, which is the degree of the H-star vector of the polytope. The H-star vector, you can think of it as the degree of these Eulerian polynomials we saw before. So it's the one on the top, on the numerator in the Ehrhart polynomial equation. Yeah, and now my point was that these polytopes, the two polytopes do coincide in some cases that we discussed, the ones for multiset permutations and the ones for the models. So before we saw this independence model here, and if I read off the polytope, it's going to be the convex hull of the unit vectors here coming from the columns. So it's going to have this form. By looking at it, it's a bit hard to understand what it is. It turns out it's just isomorphic to the square. But the problem in statistics is that these polytopes come in very high dimensions and we don't immediately know what they are. So we're looking for ways to write them down in a nicer way. And if you do that, you will see this is a square. So we know immediately what is, for example, it's H-star vector, which is the Eulerian polynomial in this case. So it turns out there's a bigger connection there. In particular, if you're looking at a generalization of so if you take your simplicial complex to be a union of disjoint cliques, like here, just disjoint cliques, then you have, for those that know what this is, that the polytope is a chain or ordered polytope, equivalently for us, for this kind of underlying simplicial complex. And therefore, the H-star is known, and it corresponds to descents of multiset permutations. So for the independence model, to go back to this, I had the independence model, which was coming from the simplicial complex with just 2 points and 2 outcomes. I look at the polytope of the model, I compute the H star, which is an invariant in Ehrhart theory for the polytope of the model, but then I can understand it in terms of just how many permutations of 1, 2 have 1 descent and how many have 0 descents. So it's just 1 plus x in this way. And this connection extends to all multisets. So to end, my future goal idea is to understand other sets of permutation where this happens. And there was a really nice one that it has been asked by Graham and Zhang. So they were doing some other set of permutations that are called split pair permutations. They're multiset permutations with some properties, like between the ones I want a 2, between the 2s I want a 3, and so on. And it turns out you start with these permutations, the corresponding descent polynomial there is going to be the same as the H star of the polytope of the simplicial complex in statistical models that is just a chain. That's called the Markov chain. So yeah, this is a very quick thing, but the idea is that the conjecture is that there's a second example of permutations of multisets whose descent polynomials appears as H-star vectors of polytopes of statistical models. And this is nice because it could give intel in both sides. Because, for example, from some other work we know this thing will be palindromic. From the statistical models, we know this polynomial will be palindromic. So we can take this information to the permutations and say, your descent polynomial is palindromic. And vice versa, it can also help us for the models. But I think I'll stop here, and thanks for your attention.
Okay, thank you very much for the talk. I will stop the recording now. Are there any questions?